All right, hello. Um, Today I want to talk about something interesting to me as a math professor. When you can learn something from a student mistake, and a student mistake which, by erroneous reasons, led to a correct answer. So let's get started. And okay, here we go. This thing is old and antiquated as I am. Okay, let's see this. And let's open this up. This is kind of embarrassing, but all right, here we go. When I was graded, I got a question from a student about an old exam where we had the following question. It was an implicit differentiation question. And the question is that if you have e to the x squared y equals 5, find dy dx. Solve for dy dx. And the student came up with the correct answer. But if you look at right here, if you look at what they did, is they took the derivative and then took the log, but they made a mistake when they took the derivative. And I'll just go ahead and put this up here. The mistake they made is when they went to calculate this, when they went to calculate, I should make this a little thicker. There we go. When they went to calculate this right here of E, and I better look at this again. Well, I'm sort of messing up here. Let's do this. When they did this, e to the x squared y, they differentiated in the exponential area. So what they did is, that when they took this, they incorrectly said that this is going to be e to the d dx of x squared y, which is wrong. But what happened if you went ahead and did this, this part really is equal to, using the product rule, 2xy plus x squared dy dx. And they also had this equal to, in this case, 5. Now, if you took log of both sides, and again, I want to make sure I know this is wrong. You have that. And then you have 2xy plus x squared dy dx. And well, what they did is they differentiated. And this is what leads you to the correct answer. So what's really going on here? And what this led me to think about is a kind of problem I actually had. If we just look at the original question here, and I said this was equal to 5, if you look at this in 3 dimensions, if you look at this in the plane, but thinking about this as a 3-dimensional function, a function who has a graph in the z-axis, a real value, this is really a level curve. Okay. And then what happens if you then took the log of both sides, then you differentiate it, and do that correctly, and the derivative of a constant is 0, we are led to the correct conclusion. All right. So, going from here to here, we took the log of both sides of the equation. Now, what I was hoping they do is I was hoping they'd start off by saying, taking the derivative of both sides, and then differentiate the right-hand side, you get 0. Differentiating the left-hand side, and then using the chain rule, we get that. And that's equal to 0. And then noticing that e to the x squared y is never equal to 0, you can divide both sides and you get the equation, which enables us to solve for dy dx. Okay? So there's kind of two ways of doing that. And they both involve finding a tangent of a level curve of the function at a level curve of the function f of xy equals e to the x squared y. And thinking about this in 3 space. And here you'd be setting z equals f of xy equals 5 and finding the tangent to a point on the level curve. Now, that's well and good. But what led me to think about this is, why does taking the log of both sides work? Well, and what that leads me to is to think about this. And math professors love to generalize, so that's what we're going to do here. So let's generalize this. So suppose you had some function of, let's say you had g of xy, real valued function, and you're interested in dy dx if g of xy is some constant, some level curve. And suppose you had a function, you're given a function f, real valued function, where you had the derivative, where you had, how can I say this? Where f is monotone. In other words, either always increasing or decreasing. That implied in that is 1 to 1. And f prime is also monotone. Oh, well, f prime is also never 0. That's important. So you have f prime not equal to 0. Then if you wish to take the derivative, so let's say you wish to take d dx of f of g of x of y equals d dx of this constant here, well, the right-hand side is 0. If you take this, what you get by the chain rule, because remember, this is a single variable function, you get f prime of g of xy. And then you'd have the chain rule version of this. So you'd need to take, and I'll just go ahead. I'll write a d dx of g of xy. I'll write it that way. So you have f prime of g of xy. And then this thing here, you take the derivative of g with respect to x. And well, I'll go ahead and write it like this. Partial g, partial first variable. So I'll just call it variable 1. Let's call it v, dx dx, plus partial g, partial second variable. I'm using this as v and w. And then dy dx. And this, of course, is just going to be this part right here is just going to be d dx of g of xy. And assuming that this is also never 0, we get the original expression. Well, that's just a 1. Which is what we would have gotten had we just differentiated this to begin with. So, um, and if you're confused about the V and the W, what you could do is you could just call this X and Y. And this part would be dx, which is just a 1. So this would be dg dx, dg dy. That's a partial with respect to y times that. And that's fine. So this is what our original task is. And when we had, in our case, our g of xy happened to be e the x squared y. So when we took the, so this is a function of 2 variables. So the partial of g with respect to v, that would be your 2x, y, and this term right here would be your x squared dy dx right here. And that was equal to 0. So that's what was going on at this place. I mean, so I guess I really got a little bit carried away by using this notation. I probably should have just called that something with x squared and y, but that's what's going on. So in our particular case, we were looking at level curves, assuming that this was a 2-variable function, a real valued function of 2 variables, and we were looking at tangents to level curves. That's what the dy dx is. So anyway, that student mistake gave me something to think about. So thanks for watching.